Hello, everybody. Thank you for, 10 minutes, good. Okay. Thank you for coming to my talk. I was very pleased Wes McKinney decided not to show up today because I was in competition for him for an audience. So thank you for coming. I want to thank the organizers of PyData to start. I've been to 2 or 3 of these PyDatas. They're my favorite conferences of the year because not only do we get to hear about interesting topics, we get great open source GitHub code from industry professionals who have very similar problems to those that we're working on. So I hope to be able to provide either one of the two, maybe an interesting topic or a few code that you can use in your daily work today. So I'm going to be talking about a correlation matrix filtering algorithm that I really like. It's due to Bouchot and Potters, but they have used a variety of other results in order to build this filter. So just for a bit of motivation, So correlation and covariance matrices are widely used as input parameters in a variety of financial models. Asset allocation probably being the most prominent. Covariance matrices are usually inputs into those. And they unfortunately sometimes will suffer estimation errors due to estimation error that can sometimes come from outliers in the data. Also noise inherent in the data, and there's a variety of other issues that can result in these estimation errors. And if you have a poorly estimated covariance or correlation matrix, that can influence subsequent results in whatever the output of the financial model you're using. Yeah? Can you make the font level up? Can go up one more. Is that okay? Okay. And so I'm going to examine one technique for removing some of this noise error that'll allow, and I'll explain how it helps with asset allocation models in particular and making them more stable, making the optimization problems that you have to deal with more stable in asset allocation. And I'm going to be dealing with S&P 500 daily data, and I'm also going to try to demo a new package called CVX-Py that I really like. It's a very simple interface to I think 6 different open source convex optimizers, and you'll see from the code that's really easy to set up your problem in CVX-Py and solve it. So here's the rough outline. So first we're going to just download and wrangle S&P 500 daily price data from Google Finance. And then next, I'm going to have a quick simulation. I'm going to simulate heavy-tailed time series sampling from student t-distributions. We're going to estimate the correlation matrix between these sampled heavy-tailed time series, these simulated time series. And we're going to look at the eigenvalues of the distribution. We'll find it has a very nice structure to it. The distribution of eigenvalues of the correlation matrix has a nice structure to it. And then we're going to review a theorem of Marcenko and Paster, which describes this distribution. And then we're going to use this theorem as a basis to design a noise filter on correlation matrices. And then we're going to apply this noise filter to this S&P 500 data. And then that's going to result in 2 correlation matrices, one raw matrix that we just estimate directly from the data, and a second filtered correlation matrix. And then from the correlation matrices, we're going to reconstruct the covariance matrices and then use these as inputs into a Markowitz type asset allocation problem and show that you don't have significant difference. So going with the more stable covariance / correlation matrix will lead to similar results, but you have more confidence that you're not going to run into numerical issues in the process. So to get started, this is first cell is just what I use to download S&P 500 data from Google Finance. So this very first ticker DF line is just a list of S&P 500 stocks. I think a couple months ago that there's a variety of places you can get this online. I just put it in a CSV file and read it in. And I fixed a start date 1/1/2010, and I'm just going to be going to I think yesterday is when I made it. So this main for loop it's basically it's the loop around a very nice function, I think, in Pandas called the data reader function. So this data reader function, you feed it a ticker, and you feed it a source, Google being one source, Yahoo Finance being another source, and you can feed it an optional start date and end dates. And That's basically it. What you'll get back is a table, a Pandas data frame of end-of-day prices for that stock from that source. You get adjusted close prices. You get volume information. You get I think 5 different fields. I don't remember all of them. I'll just be using the adjusted close prices. I think this is incredibly nice because I remember about like 8 years ago, before this was in place, I spent a good like 2 days using Bash and C to go and wget to go and build all this up myself. But now it's all been done in Pandas, so it's very easy to get end of day data. And so this main loop will extract data for all S&P 500 stocks. It only takes about 5 minutes to gather all the data. And I'm going to store everything in a single data frame, concatenate them all together, and then I just pickle that data frame. So later, if I want to open it up, I can just do it directly instead of having to rerun the downloader. Okay. So the next portion is the simulation. So here we're gonna take the simulation. We're going to take 2,000 draws, 2,000 points per time series, to represent the returns from a student T distribution, to represent the daily returns of 500 different time series. And we're going to take a student T degree of freedom parameter 5. Student T distribution, anytime the degree of freedom parameter is greater than 2, the distribution has finite variance, and that will be key to something that comes up in the future. So this is 5 was a reasonable choice of parameter. And next thing to do is we're going to compute the cumulative returns of each of these time series in order to construct the actual simulated stock time series themselves. And then we're going to plot the distribution of differences in one of the plots below. And we're also going to going to compute the correlation matrix of these time series, and we're going to look at its eigenvalues and plot their distribution. So here it is. First of all, in code. So the first line, we just set the degree of freedom parameter. Second line, we set the number of time series we're going to generate, 500. Third line, the number of points per time series. And then it takes just 2 lines of Python to do all of this. This is a wonderful thing. Yes?
Are these by construction independent?
IID, yes. These are all IID draws. So I think this is one of the really nice things about Python doing these type of simulations. It only takes a couple lines to do it. So in the first line is the random sampler in NumPy. There's this nice standard T, student T distribution sampler, and you can just specify the degree of freedom and the number of series and points that you'd like to draw. And the next line, so I put everything into a data frame, compute the correlation matrix, take an eigen decomposition of it, eigenvalues, eigenvectors, and just take the eigenvalues associated with it. So 2 lines, it's done. The rest is just plotting code. So here's the code. So this is a plot of the sample paths, 500 sample paths, as well as the mean path, which is about 0, which is what you'd expect. You see a few outlier paths to the top and the bottom that are a result of the fact that we have student T samples. They're getting a lot of these heavy-tailed draws from them, as opposed to if we were using Gaussians, for example, they wouldn't go quite that far out. Also, student T distributions are a lot better class of distributions to use to model return densities in finance. Anything you look at, if you look at rates, you look at commodities, you look at stocks, you look at any type of returns. I've never seen a Gaussian in finance. Maybe it exists. I always see something with heavy tails in it. So usually student T's or other heavy tail distributions I find to be good to model. It's 1 line per simulated time series. And then the red line is just the average. I just overlay the average onto it. So this next one, I just took a cross section of these time series at the very last point. And this is a very nice plot I like in Seaborn. Check it out. It's I think it was dist plot was the name of it. So there's a histogram underneath it. It's a histogram standard. But I love this. There's one particular kernel density estimation method called non-parametric kernel density estimation that's in both SciPy and I'm pretty sure it's in scikit-learn as well. And this is a fit using that method over the density itself. And assuming you have enough data, I think this is one of my preferred ways to estimate densities of returns, because you have a lot more degree of freedom over any parametric method that you might use. You're not now restricting yourself to a parametric class. You're using a more generic set of methods, equivalency estimation, to fit it. The one drawback of this method is the way the bandwidth is chosen is a little ad hoc. Cross-validation's better, but it takes longer. But it's still a nice just one line to call it, and just to get a quick visualization of this using the method. And the last plot's what I think is the interesting plot. So we took we have these 500 time series. We compute their correlation matrix, and now compute the eigenvalues of that correlation matrix, and now plot a histogram of those eigenvalues. And this is what it looks like. There's structure to it. It's not just it's not like uniform random. There's structure to it. One thing to note: there's a lower bound. Another thing to note is there's an upper bound, and then it's slightly skewed to the left in this case. And so it turns out that there is a theorem about this. There's a random matrix theory theorem, which I'm paraphrasing here, getting a little bit out of the true mathematical setting of it for more coherence. So here's the way it can be stated. So if x is a random n by r variable, so here n is going to be the number of points in the time series, r is going to be the number of time series, whose entries are all IID, have finite constant variance. This is why we're using this degree of freedom 5. We're not getting too small where we have infinite variance. And IID, finite constant variance, and these are the only assumptions we're going to make in the theorem. We're not making any distributional assumptions on the type of distribution these are drawn from, only these very, very relaxed assumptions. Then the eigenvalues of the correlation matrix corresponding to x are distributed by this relatively simple functional form. F of lambda equals q. Q is a constant divided by 2 pi lambda. Lambda is the variable, times the square root of a quadratic. Lambda plus, which is going to be the upper limit of this eigenvalue distribution that we saw, minus lambda times lambda minus lambda minus. And lambda is only defined in this interval, lambda minus lambda plus. And here, lambda plus and lambda minus, these upper and lower eigenvalues are only a function of q. And this constant q is only a function of n and r, the number of points in a time series and the number of time series themselves, for any distribution you like, as long as you have finite variance. And so the first time I saw this, I was rather amazed. I thought this was a great theorem. I would never have expected this beforehand, that it would be true. And this was developed by Marcenko and Paster in a pure math setting, and it serves as the main result that was an application of Bouchot and Potters into the development of this next noise filter that we're going to talk about. So here, just to check, in this next cell, I implemented this distribution and overlaid it on top of the histogram that we previously saw, and you can see it fits it fairly well. Out in the right tail, we didn't quite have a large enough matrix to fill it up, but if we get larger, we'd probably get another bin on the very end to get the last bit. Okay, so now we're going to apply this to S&P 500 data. First, we're going to do a little data wrangling. So we're going to specify a start and end date for the data. End date being, I think, like 2 days, or 10/1, October 1st. And first, we have to make sure all our time series are normalized. One of the requirements of the theorem is that they all have the same variance. So we're going to apply a normalization step to all of our time series. So here it is in the code. The first line is just an implementation of this lambda plus, which is going to be used as a threshold in the filter we're going to design next. Next part, we just read in the data if it's not already in our local variables, read it in from our pickle file, and specify both the start and end date. And then I want to, just for simplicity purposes, so make a list of tickers and compute the lengths of all the tickers. Sometimes the names haven't been in the S&P 500 long enough to where you have a significant enough data in order to do computations on. They might have only been in there for 30 days. So for purposes of simplicity, I'm just going to compute the length of all of the S&P 500 time series that we're looking at. And we're going to take the mode of all of those, which will correspond to the ones that have been in the index the longest. And then only series that realize this mode length I'm going to keep. And so it'll get, we're rough with like 460 times series roughly, but not quite 500. This way everything's uniform and nice. I don't have to worry about any filling any gaps or interpolation or such. And then the next little block's a normalization step. So we just demean each one of these time series and we divide by its variance. So all of them have variance 1 and compute the returns for each series. So now we have normalized returns for each one of these 460 or 70 so series. That's what this block does. Okay. That's the returns. Everything's with returns. And so here's the part of the filtering construction. So we're interested in this theorem applies to correlation matrices. So the correlation matrix is defined right here. If x and y are 2 time series with components x sub I and y sub I, the correlation's the covariance of x and y divided by the square root of the variance of x times the variance of y. And here you just use the unbiased definition for the covariance. And variance of a variable is the covariance of the variable with itself, and I just find the mean out there to be complete. So if you let rho be let rho denote the correlation matrix, I'm going to call its eigenvalues lambda sub I, and the corresponding eigenvectors for each lambda sub I, e sub I, and order the eigenvalues. Lambda 1's the largest, going down to lambda n, just for some notation. So we can decompose, do an eigenvector decomposition of the correlation matrix into sigma, lambda, sigma inverse, where here sigma is just the collection of eigenvectors for the matrix, and lambda's diagonal matrix that contains the eigenvalues, sorted in order from lambda 1 being the upper left component all the way down to the lambda n. And there's some issues. I was getting like very slight imaginary parts when I was doing this. It would be like 1 plus 0.05 e to the minus 13i. So I just applied a modulus over everything, absolute value, in order to get rid of these small imaginary parts to guarantee everything was real, but shouldn't significantly affect anything. And here it is in code. So we have this return data frame, drop nans there. Creating feedback. Okay. Dropped all the nans when we're computing returns. I think that we had one row of nans, so just get rid of the nans, and then use the core function and Pandas for a data frame, and then compute the eigenvalues here and the eigenvectors using this linear algebra portion of NumPy la.eig, and then finally I just map the absolute value function over the eigenvalues in order to make them all real valued.
Just doing a single factor model, or yes, what do you do?
No.
Covariance S&P 500, right?
We're right now computing the correlation matrix of the S&P 500, but then we're going to filter that and remove the noise out of it. But there's not just one factor. We're going to keep all 500. And so here's the idea behind the filter. So we have a 500 by 500 matrix of 500 eigenvalues, and so usually if you're from the PCA world and you have like high dimensional data, your first thought is, well, let's do a PCA decomposition of data. I want to figure out, where do I cut off? Maybe only the first 3 eigenvalues correspond to 99.9% of the variance explained, and then the other 497 don't matter. In some financial contexts, it's very easy to know where to put this cutoff. For instance, if you look at the variations of the yield curve, or if you look at the variations of a commodity futures curve, you can see it's almost always 3. And usually 2 gets you like 99% of the way there, but it's clear you can either put your threshold after 2 or after 3. If you're looking at equity portfolios, in particular long-short equity portfolios, and you do the same thing with, say, like 500 names, it's not so clear. You tend to have these nice, like, sort of decay functions for the eigenvalues. And do I put it after 10? Do I put it after 20? Do I put it after 50? What do I do? And so the motivation behind the construction of this correlation filter is, let's use this lambda plus value as the threshold for it, because that, if the matrix was purely random, then lambda plus would be the largest that any noise eigenvalue could be for the associated matrix. And so we decompose this list of eigenvalues, these 500 or roughly 500 eigenvalues, into a lower portion, lambda 1 through lambda k minus 1, and an upper portion, lambda k, all the way up to lambda n, where we split it right at this lambda plus eigenvalue, which we compute, which is only based on these two quantities again, one the number of time series and the other the length of the time series. And after doing the split, everything that's below this lambda plus we're going to call noise. And we're going to take an average of all those noise eigenvalues, and we're going to replace each of the noise eigenvalues with this average. Why do that? Well, it's a correlation matrix. A correlation matrix has a trace, which is equal to the sum of the diagonal, which is going to be the dimension of the matrix of 500. So if I would ever change that trace, I would no longer be a correlation matrix for this number of variables. So a trace is something you want to preserve for a correlation matrix. And that completely fixes the noise portion here. So all these noise portions are lambda tilde, and then lambda k through lambda n. These are kind of the eigenvalues that have some information content that are non-noise. And traces preserved. And so here's the filter, just another few lines of Python. I love Python, by the way. So it's a couple lines you can do like anything in Python. I'm not a computer scientist by training. I'm more of a mathematician, physicist. That's love it. And so here's the filter, the first list comprehension. The second one is just creating a new list of noise eigenvalues, and the third one's constructing this list of new these new noise eigenvalues, these lambda tildes plus the information eigenvalues. And so now we have a new matrix, lambda tilde, and from that we're going to use the original eigenvectors to reconstruct this correlation matrix, this equation right here, the sigma lambda tilde, sigma inverse. And so it turns out when you do that, you don't get a bona fide correlation matrix. So you're pretty close, but it's not quite there. The first thing I do is symmetrize. There's a little numerical error that comes in, so it's not quite symmetric, but it's do the symmetrization, rho tilde plus rho tilde transpose, and take half of that. And then the next issue is that there aren't necessarily ones on the diagonal of this new correlation matrix, so it's a little bit off the correlation matrix. But fortunately, there is open source code to solve the optimization problem that allows us to find the nearest correlation matrix. I put it in quotes because we have to say what we mean by nearest. And so in this setting, the nearest correlation matrix is the one that solves this particular optimization problem. So we want to minimize over some space of matrices S, X minus this rho tilde 1, the symmetrized version of the reconstructed matrix. But S is going to be any invertible matrix that is symmetric, X equals X transpose, that has ones on the diagonal, and is positive definite, all positive eigenvalues. And the norm here is the so-called Frobenius norm, which is just the sum of the squares of the differences of the matrices we're searching over X and the matrix that we have. And there's the definition of the norm. So it's nice that Mike Croucher, I believe is how you pronounce his name, has already implemented a function that is amenable to solving this problem that I'm just calling. It's called near core. It solves exactly this problem. And so here in this RC mat, we're just reconstructing this rho tilde, and then symmetrize in the next line, and then find the nearest correlation matrix. It's an iterative optimization procedure. I just set it to be, so the max iterations to be 1,000. It converges fairly quickly. It only takes a couple, I think it's in milliseconds roughly to solve this problem. It's rather quick. And then that's it. Now we have this n-core new filtered correlation matrix. It is a bona fide correlation matrix. And we can look at a bit of some information about this. If you actually compute its eigenvalues, they look very different than those of a random matrix. The largest eigenvalue is 186. So it's a correlation matrix for roughly 500 stocks. So the sum of all the eigenvalues is roughly 500. And so the bulk of the weight is in this first eigenvalue. And it is the eigenvalue in the PCA context that corresponds to this market factor. The market is the largest component. And then you go down a little bit, 14, 9, 6, 5. And then roughly the top 10 eigenvalues here are significant according to this random matrix result. But if you overlay this distribution of eigenvalues, this is all the eigenvalues right here, all the small enough ones overlaid with the this Marcenko Paster density. The lambda plus upper limit for this filter is like roughly 2.5. So everything lower than these top 10 gets filtered away and replaced with its average. So even though there was like 500 to start with, we've broken it down to about a 10-dimensional problem. And just wanted to do a few plots here. I don't know if there's too much information in this plot, but I think Seaborn's heat map plot is really cool. Check it out for the Seaborn's correlation matrix heat map plot, or any matrix heat map. And here's a plot of the differences. So I have this filtered correlation matrix and the original correlation matrix. I just took the differences of them and plot the difference matrix in order to see what are the values large, are they small, are they scattered, is there any sort of like pattern to them. And there's a few specs where they're bigger than like 0.5, but most of all they're sort of in the middle. If you plot a histogram overall of these differences, here's what it looks like. It's heavy-tailed itself. You see like a few of these larger ones at 0.1 and minus 0.1, and then in the middle, they're highly concentrated around 0. Okay. And so for each of these correlation matrices, next thing we do is just reconstruct the covariance matrices by multiplying through by these square root of variance terms. That's what this block of code does. And we reconstruct the covariance matrices because we want to get to this asset allocation problem. So there are tons of problems that require covariance matrices input in finance. This is the one that I think is probably the most widely used Markowitz optimization or variance of Markowitz optimization. So I didn't want to stick with vanilla optimization. I want to add on an extra term here. So this is the type of problem we're trying to minimize. We have this quadratic form, WT sigma hat W, where sigma is the covariance matrix. And then minus these lambda, mu is the expected return vector times W, but then plus this regularizer term, gamma, with the L1 norm on the weights right here. So sometimes one of the criticisms of this model is it tends to focus a lot of the weight than say just one or two, a few of the stocks. And you can add on a penalty term in order to get more diversification for that. And so we did that in the next line. We're going to be varying lambda subject to the constraint. The sum of all these W sub I is 1. I choose mu to be 0.0003 because it's good. Don't ask me why. I like 0.003 to get good results. But as you increment it or as you increase it or decrease it, you just change the influence of this final diversification penalty. And so here's one of the things I just really wanted to show you. CVX-Pi is a very nice interface on top of CVX-Opt, I think ECOS, SCS, and there's several other optimizers. And the way you set up one of these problems is in this following for loop. You say what you want to optimize over the variable. You set up the objective function. Want to minimize a certain quadratic form, this x in the covariance matrix, times second terms of this expected return term, and the last one's the regularization term. Say what your constraints are, and then you do problem, set up the problem, and then you do solve, and then that's it. And what the CVX-Pi does for you, first of all, it checks whether or not you have a well-defined optimization, convex optimization problem. If you don't, it will say, no, go find another optimizer for whatever you're solving. If it does, then it will branch. It will symbolically try to figure out what type of problem you have, and then send it to the right algorithm, find the results, return back the weights, and return back a bunch of other information associated with the optimization. Check it out. Very easy to use. Very well done. It's built on top of a lot of optimizers that have been around for a while. So I'm pretty confident in using it. It also saves the pain from having to contort your problem into somebody's very specific form for their optimizer, where you have a lot of error due to potential math algebra errors. And then I'll just show the final. So here we run this optimization problem for varying lambdas on both the unfiltered and non-unfiltered correlation matrix. And then next part, we plot the efficient frontier for both. And the main takeaway is that both of them are in green and blue, but they're almost exactly the same. So even though we removed 490 of these eigenvalues out of roughly the 500, and then replace them with the average, we get roughly the same results, which is a good thing, because everything's now being done with a more a nicer correlation matrix where I don't have these like tiny eigenvalues that are like 10e to the minus 15, which usually result in lots of numerical issues through other parts of the process. And I think that's all. Here's my email and a few references. The talk's on GitHub, and it should be in the URL. Thank you. So I think if there's, I think that the normal overall, it'll be smaller if they're more equally distributed than if there's only one or two that gets the bulk of the concentration. I believe so. You could do it. I'm kind of hesitant to reconstruct a covariance matrix from something that's not a correlation matrix. So when you do this process, you sort of get like slightly out of the space of correlation matrices, but just barely, and you're just perturbing it like right back in to find the nearest one. You could do it. There's nothing that's wrong. That's like technically an issue here, but I'd rather work with a bona fide correlation matrix than one that's not quite one. I haven't tried it myself. I like it though because it's like a very Bayesian idea where you sort of like take this combination. The shrinkage estimators are taking a combination of the actual data plus what you sort of expect, and but it's a good idea.
Speedwise is probably okay.
Yep.
Like shrinkage estimator will give you a quicker answer. Do it real time.
Very true. And I've had several of my colleagues, so I haven't looked into it, but ones that are more experts on this, and as well as like more Bayesian statistics, tell me that they've worked with shrinkage estimators and they always have some problems with what they're doing. I can't speak to it to myself though. I haven't worked with it, but it seems like a good idea. I haven't looked at it.
How are you going to decide the lambda plus if you are like applying the demand decay on your data? I would like intuitively, I would think the spend is going to be smaller, so you will expect a bigger lambda plus, but then what are you going to expect it to be?
So the only thing for lambda plus that we care about is the number of points in the time series and the number of time series.
When you apply a demand decay, the effect length is actually smaller.
I'm sorry?
When you have a decay, if you value more on the recent data and then less on the previous data, then the real effective length is actually smaller than n.
That's very true. So you can use these sort of like weighted average covariance estimators, but then you have an effective n. Like even if I'm using a weighted average, like a exponentially moving average estimator for the covariance matrix, then if it's 100 points, but with this, the effective number of points is like 20 or 30. So that's something that you could probably adapt this to plug in for n. But
So this will make the lambda plus a lot bigger than what it is now.
it would. And another interesting point is that it kind of tells you like how many points in the time series you need in order to get good estimates on these matrices. A lot of times in finance, we're going to be using like 200 data points to estimate a 500 by 500 matrix, and from the statistical point of view, that's bad because you just have so much noise in the estimator itself. It's not going to work. If you try to apply one of these filters in that case, you're basically just going to filter out everything, and you're not going to be left with anything in the problem. So it's.
Thanks a lot, Steve.
Thank you.